Welcome everybody to Integrated Math 3. In today's episode, we're going to be discussing chapter 9.2.1, which is transforming trig graphs vertically. And so before we get into what the transformations are going to look like, especially because we probably already have an intuition as to how they're going to work, let's go ahead and talk about what happens when we graph the trig functions not in a super detailed way. Because up until now, we've only been responsible for graphing them really detailed. So I'm going to show you what we are looking for when it comes to just graphing the bare bones of a sine graph. And of course, we know that these graphs can go on left and right horizontally forever. So what I'm going to do is I'm going to just graph this thing on a window from negative 2 pi to 2 pi. And I have to restrict that because otherwise I'm going to graph forever and we don't really want that. What I'm going to do is I usually go ahead and start off at the origin because that's where sine is going to start. And I know sine's behavior, and you're going to want to pay attention to how I say this. The sine is going to start at the center, go up, down, and then up. And then, of course, on the left side, it's going to go down, up, and then, whoops, that didn't even look right, down, up, down. And that's supposed to be mirrored, but of course I think I probably lopsided my coordinate plane, but I'm hoping we understand that. Well, from here, notice the window I'm using from negative 2 pi to 2 pi. Well, remember, when it comes to graphing, right now I'm graphing in radians, so ordinarily this could also be seen as negative 360 to 360, but radians is usually going to be where we go. So I'm going to go ahead and slam down this point here. Now remember, this is one period of sine already because we're crossing the x-axis in an upward rising kind of way. So while this used to be considered 360 degrees based on the sine graph that we learned a couple of videos ago, I'm going to call him 2 pi radians for that one. Now this part here, which used to be at 180 degrees when we last did sine in degrees, that's now going to be, well, 180 degrees is half of 360, which means this is going to be pi radians, right? Half of 2 pi is 1 pi. This point here, I call this halfway between the halfway. That's going to be pi over 2. And now to get to this third point, I'm just going to do a count. This is 1 pi over 2. Technically, pi is 2 pi over 2. This point here is going to be 3 pi over 2. And 2 pi is really 4 pi over 2. So hopefully the countdown of that makes sense. I'm going to do the exact same thing over on the left side. This is going to be negative 2 pi. Halfway is negative pi. Halfway between the halfway is negative pi over 2. And 3/4 of the way is negative 3 pi over 2. And of course the sine will go as far up as 1 and as down low as negative 1. And hopefully that makes sense as a parent function for sine. The points that we're going to be most interested in are going to be what I call the middle points and the humps and the underlumps. And that's going to be what we are interested in. So now what I'm going to do is I'm going to go and take that idea and apply it to cosine. All right, let me go and just draw this coordinate plane here. And again, I'm probably going to do the exact same window of negative 2 pi to 2 pi. And so from here, again, I like to draw the curve first. I don't know if you noticed, I like to draw the curve first and then I draw in the points second. So if you guys remember, cosine started high, went way low, and jumped up way high. And then from here, it's going to go and do the same thing on the back end. And so from here, remember, one period from one hump to one hump. That's the repeat of graphical behavior. We have 2 pi here halfway at the low part, so halfway between 2 pi and 0 is pi. Halfway between the halfway is going to be pi over 2, and 3/4 of the way is going to be 3 pi over 2. I'm going to replicate the same thing on the other side. These graphs are going to kind of intersect here, so 2 pi negative here. Halfway is negative pi, halfway between the halfway, and 3/4 of the way. And that's cosine right there. And right now I'm going to take on tangent. So tangent, y equals tangent of x. Again, I'm just going to go from negative 2 pi to 2 pi. Now this one here is a bit different. Tangent, I actually do put in the points first because of the way it looks. So, I think the most important thing with trig is just to be flexible. Don't feel like you have to do the same thing all the time. And so here we go. Hopefully you will remember that every pi over 2 is going to be a vertical asymptote. And then these guys looked almost like cubic functions. They look like these snakes here. And they would pass through. So hopefully this is a familiar image. And there you go, like that. That's tangent. So why did I graph all of these? I graphed all of these because these are effectively the parent functions of sine, cosine, and tangent. So when we start hearing words like parent function, it is time to start thinking of transformations. So let's talk about the first transformation, and we're only going to do the vertical ones today. If I did y equals sine of x plus 1, if you want to, go and pause and think about what that would do to the graph. Think about where that plus 1 is, and then what that would do to the graph. The plus 1's on the outside, so I'm hoping that everyone remembers that this is a shift up by 1. So how does this affect the graph? I call this thing a vertical shift. I abbreviate that as VS, and I just call 1. What you're going to find with how I do this is I like to make lists. So the way I'm going to do this is I'm going to look at sine. Notice how it starts at 0, goes as far up as 1, and as far down as negative 1. Now I'm shifted up by 1. So I'm going to shift this thing up by 1. What I do is I draw almost like a pretend new axis right here. And I'm going to label him as 1. Now remember, sine from its center, right? That's what this is doing. That vertical shift is shifting the center up by 1 and all the other points along with it. Now, from this center, it's going to go up 1 and down 1. So hopefully it makes sense that this graph is going to go as far up as 2 and as down low as 0. And then it's going to do the exact same thing that it did before. It's going to go up and then down and then up. Now, what I like to do is I don't graph normally between negative 2 pi and 2 pi. This is just for our own reference for the parent function. What I usually do is I usually do negative pi over 2 to 2 pi. So I do a period and a quarter like that. And then, like I said, I graph first and then I label afterwards. So this is going to be 2 pi, halfway is pi, halfway between the halfway is pi over 2, and 3/4 of the way is 3 pi over 2. Back 1/4 clock is negative pi over 2, and that is sine of x plus 1 on the outside. So hopefully that makes sense that a plus 1 would shift it up by 1. Let's go and see what happens with the next graph here. If I did y, let's say y equals cosine of x minus 3. So again, minus 3, what am I thinking? I'm thinking that my vertical shift is negative 3. So I'll go ahead and create my coordinate plane. I'm going to go ahead and make it a little bit top heavy like that. I'm going to vertically shift this thing down by 3. And notice how I'm just I really am at this point once again graphing approximately and labeling accurately. That negative 3 is my vertical shift. Remember, cosine, he only goes as far up as 1 and as down low as negative 1 also. So very much like sine, from the center, he'll go up 1 and down 1. So hopefully it makes sense that I'll go as far up as negative 2 and as down low as negative 4. Cosine starts at the high point. He's going to scoop way down and then go back up to his high point right there. I'm going to do 1/4 clock backwards. And now I'm going to ask where that is. That is the end of one period. That's going to be 2 pi. Halfway is pi. Halfway between the halfway is pi over 2. 3/4 of the way is 3 pi over 2. And then this quarter clock back is going to be negative pi over 2. So hopefully that makes sense in terms of how cosine is going to look with a vertical shift of negative 3. So hopefully the vertical shifts have made sense up until now. and then we can kind of make a generalization as to what that's going to be. Again, this is all stuff that hopefully is stuff that we have seen before. So let me go ahead and make some room, and then I'll graph another one. I'll be right back. The next transformation we're going to talk about is the vertical stretch. So from here, if I do y equals, let's say 4 sine x, and let's say versus y equals sine x. Well, let's take a look at the parent function one more time. The parent function here starts off at 0, and he goes up, down, up, and then maybe just a little bit back like that. Most important thing to understand is that it goes as far up as 1 and as down low as -1. So hopefully this will make sense, that if I do 4 sine x, it's not going to go as far up as 1 and as down low as -1 anymore. It's going to go as far up as 4 and as down low as -4. And it's going to behave the exact same way. So again, notice how I'm just kind of labeling it accurately, and I'm graphing it approximately. And I do my quarter clock backwards. Again, I'm going to label these. 2 pi, halfway is pi, halfway between the halfway is pi over 2, 3/4 of the way is 3 pi over 2, back 1/4 is negative pi over 2. This vertical stretch that we accompany with sine or cosine, this is what's known as amplitude. And amplitude, what it does is it literally vertically stretches our wave function. So if you ever get a chance to play with like an AM radio and you get to see its frequencies, and you get to see its waves, then what happens is if you stretch the amplitude, the waves look further apart vertically. So that's the basic definition of amplitude. There's a lot of different kinds of practical applications for it that I won't get into in this video, but hopefully the idea of amplitude makes sense. So let's go and do another one. If I did y equals cosine x, let's say with a 3 in front of it. Again, cosine normally stretches from -1 to 1, but this time it'll go as far up as 3 and as down low as -3. And again, remember, cosine starts at the way top, goes way to the bottom, and then back up to the top. Again, I'm going to do a quarter clock back. And again, remember, at the hump, it's going to be 2 pi. Halfway is pi. Halfway between the halfway is pi over 2. 3/4 of the way is 3 pi over 2. Back 1/4 of the way is negative pi over 2. So hopefully that makes sense for cosine. Usually I make a label here called amp, and it's called 3. In the sine function, the amp would have been 4. Now, with tangent, there is no amplitude, because with amplitude has to be locked between two particular values. So if I do, say, 2 times tangent of x, do not label the amplitude as 2. This one, if you were to label the amplitude under this list, you would write none. So how does the 3 affect tangent? Well, all it does is it does what you would normally expect. It makes the graph skinnier. And so all you would have to do is make it just a little bit thinner and grow a little bit faster. Notice how I'm not really that close to the asymptotes on this one. And then you might want to just label a point up here. Now remember, with tangent, pi over 4 used to give us a value of 1. But with this 2 out in front, now you can say that pi over 4 will give you a value of 2. And with that little extra point right there, that is enough to convince me that you know that the tangent is being stretched by a little bit more. So most important thing about tangent is that it has no amplitude and that it just stretches the graph like it normally does. If this was a cubic or if this was a quadratic, it would do the same thing. Of course, no graphical transformation would be complete without the introduction of something that looked like this. So again, I go back to y equals sine x, and remember the graphical behavior. This goes from the center and it goes up, down, up. So take a wild guess as to what this graph is going to do. It's going to start at the center and it's going to go down, up, down. And then the quarter clock is going to be above the x-axis this time. And of course, that's going to be 2 pi. Halfway is pi. Halfway between the halfway is pi over 2. 3 pi over 2 is 3/4 of the way. Negative pi over 2 is quarter clock back. It goes as far up as 1 and as down low as -1, just like before. So the upside down graphs, they just upside downify the graph just like we do with normal functions. So let's put all of this stuff together and then we will see how this goes. So now that we know all the basics, let's see what happens when we put everything together. So I'm going to go ahead and do y equals, say, 4 sine of x minus 3. So I like to make lists when it comes to trig graphing. So I'm going to say the vertical shift is -3. The amplitude is going to be 4. So what does that look like? I'm going to go and graph this thing. I'm going to do the vertical shift first. That's going to shift everything down by 3. So that's going to be -3 here. Because my amplitude is 4, that means that from -3, I'm going to stretch up by 4 and down by 4. Hopefully it makes sense. That means that the top of this graph is going to be a 1. The bottom of this graph is going to be -7. Sine starts in the center. It's going to go up, down, and then up. Quarter clock backwards. And of course, this right here is 2 pi, 1 period. Halfway is pi. Halfway between the halfway is pi over 2. 3/4 of the way is 3 pi over 2. Quarter clock backwards is negative pi over 2. And you're done. You have done a vertical combo graph right here. So let's go and do another one with cosine. And I think that might wrap us up. So y equals, say, -3 cosine x plus 3. Okay, let's see what happens here. My vertical shift is going to be 3. My amplitude is actually 3. Amplitude can't be negative, so please don't write -3 right there. I'm going to go and get my graph ready. And I'm going to go ahead and shift up by 3. And because my amplitude is 3, it's going to stretch 3 in every direction, which means it's going to go as far up as 6 and as down low as 0. Now, cosine normally starts at the top, goes way down, then way up. But this cosine is upside down, so it's going to start at the bottom, go way up, and then way down. Hopefully that makes sense. The cosine is just upside downified. And so again, where's the period? At the low point and the low point, the two underlumps here. So 1 period, 2 pi, halfway, pi, halfway between the halfway, pi over 2, 3/4 of the way, 3 pi over 2, quarter clock back, -pi over 2. So that's putting it all together. Hopefully this makes enough sense with the vertical transformations. As always, please leave comments or questions in the comments area, and I will see you all in the next episode.